While it is possible to handle different conditions and situations in a Haskell program using if-else type statements, they will often end up being deeply nested and can sometimes be a bit unnatural for the paradigm that we're going for in functional programming. So in Haskell in particular, there are several different structures that are available to handle different conditions and different possibilities within our programs. One of these is pattern matching. And so if we wanted to handle a set of different possible patterns of what our data might look like or what a particular value might be, then we can use a case statement. This is somewhat similar to a switch statement or a nested if-else statement in other programming languages, but like most things in Haskell, it results in an actual single value. So it's just an expression and it results in a value. So what we state is we state case and then some expression of, and then we state a pattern for it. Things like what our data's value might be or what our data's configuration might be. And then we give an expression that will be the result in that particular case. And we can list multiple of these patterns, each with their own resulting expression. The first pattern that matches is the one that will be used, and it's the only one that will be used in that particular circumstance. So if there's a more general pattern that would have matched later, but we match a more specific one up earlier, then that will be the one that's used. And that's typically the order you want to go in, is sort of from most specific to least specific in these. We can also capture and name parts of the patterns that we're using. For instance, here's a case on a list that, in the case of the empty list, it returns us 0. In the case of a list with a single item, a singleton, it names that single item x and then gives us x plus 1 as a result. We also can ignore particular items in our data by using the underscore. So this says I don't actually care what the value is for that list. Give me a -1. It's sort of a last, most general case. We will get exceptions at runtime if no pattern matches a particular situation that we've been given. And we'll see a few examples of that where there weren't enough patterns written to handle all possibilities, and therefore we'll get some exceptions. There's also special syntax for function definitions that we can define a function to handle a particular pattern. What it tends to look like is it looks like we defined the same function multiple times. But what we're really doing is we're defining that one function to handle multiple different possible situations. And we'll look at some examples of that shortly. There's one other piece of syntax that I want to pull out for us here, and that's the @ symbol. We can use that to name a variable for the entirety of a pattern. So if, for example, our pattern was that we were taking a list and it would have some head and some tail, we can name the head and the tail similar to how we named that item X here and we're able to use it. Well, we can also name the list L itself and be able to do things with L inside of the expression that results here. So we see that the list we were given is 1, 2. Therefore, L will be the whole list, 1, 2. X is the head, which is 1. And tail, T, is the tail to the list containing 2 here. So let's look at a few examples of pattern matching functions. Here's a pretty standard one, factorial. We've written it recursively still, but we also wrote it to use patterns. So the base case is expressed as factorial of 0 equals 1. We're able to use the specific value of that parameter n and say, if that n is 0, well, that's easy. We just give 1. Otherwise, for any general n, then we return n times factorial of n minus 1. What this implies, sort of, is that any function you've written so far actually uses pattern matching. It just uses the most general pattern of when the parameter is any value. So that pattern is shown here the same as if you wrote a typical one and maybe or a non-pattern based one and maybe used an if statement in here. Here we're letting the patterns do the if part for us. Here's a length function that says if I'm given the empty list, then I will result in 0. Otherwise, if I'm given a list that's a head and a tail, then I will return 1 plus the length of the tail. It's worth noting that the tail in these patterns can be an empty list. So this does handle the singleton. If x is the only value and the tail is an empty list, that's okay, because we're just going to call one more time and result in 0 at our base case there. And again, the order matters on these cases. If I had put factorial of 0 after factorial of n, I would never actually reach the factorial 0 case because factorial of n, any number, is so general that it will catch the factorial 0 and handle it before we're able to reach the factorial 0 if it was down below. Just for the sake of showing the syntax, here's another length function that uses case instead. So length 2 takes a list, and then we do a case on that list where if it's the empty list, we give 0, just the same as up above. And here we've done something a little different, and that is we kept the name for the tail, but we didn't have to give a name for x because we don't actually use x in either of these cases. So we can save having the variable named and not worry about it conflicting with some other x we might use elsewhere. We just say it's something and the tail, and then I'm going to call recursively for the tail. And both of those have the same signature. They take some list of some type, and they give out a number type A. Both of them do the same thing. Here's a function called more than one that uses pattern matching to guarantee that there's more than one actual item in a list. Remembering that the first thing will be a head, and then the next thing would be the head of the tail of that, and then the last thing would be the tail. The tail is again allowed to be an empty list, so this could be 2 real items and an empty list, and that's okay. That's true. That's more than one. Or it could be 2 real items and a non-empty tail. That's okay too, because that is also more than one value. Whereas for everything else that doesn't fit this pattern, singletons or empty lists, then will result in false. So this one does exhaustively handle all possibilities, even though we don't explicitly show a singleton or an empty list for it. Here's a function that is called getLast that's aimed to get the last value from a list. And that's easy to do if the list is a singleton. We just name that value x, and we return that x. And if the list is some head and some tail, then we can call getLast recursively on that tail. So this looks like a good function on the surface. It handles the singleton case, and it works its way down to the singleton case. However, its patterns are not exhaustive. They do not handle all possibilities because there's no possibility to handle a truly empty list. We can handle singleton, we can handle something and then a tail that might be an empty list, but we had at least one something, but we don't handle the empty list. And the return type looks fine. The function will work fine when given values that do match its patterns. We won't know something is wrong until we try to evaluate that function with something that does not match any of its patterns. So this can be very deceptive and lead to bugs in your code that you don't realize are there until much later. Here's a recursive and pattern-based append function that will take two lists and append the second list to the first list, making them all one united list. So if we ask to append stuff to the empty list, well, we can just return that second list, the stuff that we were trying to append. That's pretty easy. And if the first list is a non-empty list, it has some head and some tail, then we can do X combined with the result of appending the tail and L. So it's appending L to the tail. So it's going to, in this case of this 1, 2, 3, and 4, 5, 6, two lists shown here, it's going to pull off the 1 and wait to attach it to whatever the result is from the rest. It'll pull off the 2 and wait to attach to the result. It'll pull off the 3 and wait to attach to the result. The result, now, because it would be the empty list on the left-hand side, will just be L, the 4, 5, 6, and then it can return back and attach 3 to it, attach 2 to it, attach 1 to it, and get this resulting list. Its type is pretty simple. A list of type A's and a list of type A's results in a list of type A's. I've also written a reverse function here. There's a simple reverse that takes a list, and then that reverse calls to a helper function. That helper function takes our original list and some accumulated result, which starts off as the empty list. And so if we're given the empty list, whatever our accumulated result is so far, we'll just return that. And otherwise, if it's a non-empty list, then we will call recursively on the tail and add to our accumulated result. And this makes our function tail recursive, so we can get some of the benefits of having a tail recursive function. We use it as a helper inside of the regular reverse so that someone doesn't have to provide us with a starter for our accumulated result, and that's nice to do. We'll see later on some ways that we can even hide the helper function so that someone's not confused about which of the reverses they should be using. If we, for instance, packaged this up into a module, then we have ways to hide those helper functions that we'll see in another lesson. Here's a pad function that takes some list that has a head and some tail and a number n. It's trying to pad out a list until it is of size n. So if the length of our list is less than n, then it will recursively call pad, repeating x, the head. You see it repeats the head of the list however many times are needed until the list's length is correct to match that padding number. If the list's length is correct, it's greater than or equal to n, then we'll return just that list. And in all other situations, which really only means the empty list, then we'll return L. Next, we see a filter function that takes some low and high for a range and filters out numbers that are not inside of that range. So if the head of the list, X, is between that low and the high, then we build a singleton list with that. Otherwise, we have an empty list, and then we combine that with the result of recursively calling on the tail. But if the list is empty, we don't care what low and high are. We're just going to result in an empty list. So again, that gives us a base case here. And you can see that works just fine. It takes two ordering variables there and some list of that same type, and it results in a list of that same type. Here's another one that can be a little tricky. This is a same function that checks if two lists are the same. Well, we definitely want to make sure that we handle empty lists, so we've got a case for empty lists, and we say true because empty lists are equal to each other. Otherwise, we take the head X from one and the head Y from another, and their two tails. If X and Y are the same, then we will go ahead and recursively call on the two tails and make sure that everything in those are the same. This again can look like I've handled all situations, but what I didn't take into consideration is that only one of those lists might be empty and the other one might not be empty. So I needed to handle an empty list underscore and an underscore empty list case. And I didn't, and I find that out at runtime when I'm given a list that's empty and a list that's not, or even if I was given two lists that were of different length, I wouldn't reach my base case there. So the patterns can look exhaustive again, but might not be. They might not cover every case. There's another type of approach that you can take to handling different situations when defining functions, and those are called guards. So you may have noticed that with the patterns, we are a little restricted in what kinds of things we can check and what kinds of things we can do. We can check if a list has one item or two items or a few things like that. We can check if a value is 0 or an empty string or single values like that. But if you wanted to check for a range of possibilities or some complex condition, then patterns are not going to be the most friendly for that. For instance, if you wanted to handle multiple negative numbers, you would need to write a pattern for each of those negative numbers. But with guards, you can express a condition, much like an if statement, and then you give what the expression is that will be the result of the function in that case. So you give the name of the function and the parameters, not an equal sign, because you're going to use a bar and then a condition, and then say what the function is equal to in that particular case. You can list multiple different conditions, and then you can list one last condition that catches anything else, writing otherwise, and then an expression that it will be in that case. So again, the first matching rule is the one that's used, and there will be an exception if none of our conditions match. Though if we use otherwise, we really should have a condition that matches always. What we can't do is we can't capture variables or name variables like we did in the previous one. So we will have to take things out of a list by using head or tail or indexing or stuff like that. On the bright side, we can call functions, we can evaluate complex expressions to test our conditions there in ways that would not have been feasible for patterns. So here's a max function that takes an x and a y. Notice there's no equal sign here. It says if x is greater than y, then my result is x. Otherwise, my result is y. I could have just as easily written this as x less than or equal to y instead of otherwise. But the otherwise is nice because it clearly shows that it handles all other possibilities. You can either logically think it through and make sure you handle all possibilities, or you can use otherwise, but be careful with it in case there's some possibility you didn't consider and that isn't properly handled by that otherwise. So we can see that the max of 3 and 5 would give me 5, the max of 1 and 9 would give me 9, the max of 9 and 1 would also give me 9, and if the two numbers are the same, that will fall into that otherwise case as well, and it will give me the second number, which is the same as the first. So here are a couple of examples using guards for some basic functions. This one's sign tells us whether a number was negative or positive or 0. So if x is less than 0, it boils it down to -1. If x is greater than 0, it boils it down to 1. And otherwise, in other words, if x is equal to 0, then it returns us 0. The sign of -23 gives me -1. The sign of 50 gives me 1. The sign of 0 gives me 0. This is looking good. So I decide that I want to write an absolute value. And rather than having to do the different comparisons of, whether it's positive or negative, I can just use sign. I can call the sign function on n, my parameter, and I can say if the sign is greater than 0, then I return my number n because it's already positive. If the sign is less than 0, then I negate my number n to make it positive because we know it was negative already. And this looks okay. This looks pretty good. We're handling the two important cases for absolute value. Absolute value of 4 comes out as 4. Absolute value of negative 4 also comes out as 4. This is good until we hit the condition that's not handled. The absolute value of 0 is not handled. If sign of n is 0, I should be doing something, for instance, giving 0 as my result. So an otherwise would have handled that, or a specific case for when sign of n is 0. I'll show a little bit of a more interesting set of conditions for the guards here, using the example of a concatenate function that will take a list of lists and combine them into a single list. So if the list that I'm given is the empty list, then the concatenation of it is just the empty list. So null, you'll remember, is a function that tells me whether a list is empty or not. This is similar to a pattern that just showed the empty list there. So sometimes we do things with our guards that are equivalent to what we would have done with patterns. Here, I'm asking if the head sublist of L is an empty list. So this condition would not match the 1, 2 list while that was our head, but it would match this empty list here, and it would say, we don't really need to do anything in particular, we'll just concatenate the remainder of L, the tail of L. Otherwise, if the list at the head, the sublist at the head, is not empty, then we will call append with that head sublist and append it with the result of calling concatenate recursively on the tail. So we will merge, for instance, the 1, 2 with the result of calling concatenate on the 3, the empty list, and the 4, 5. And we can see we get good results for this with the example given here, the empty list, a list with only a single sublist. It works nicely, and it's able to do some sort of more complicated statements, even though we're trying to do this in sort of this limited left-hand side. It can call a function on the result of a function, which the patterns can't necessarily do. But it's also a little more verbose than the pattern in the respect to having to say null L rather than just matching to the empty list. So there are some positives and negatives for guards and patterns both. In both cases, the order matters, so this means that they can be used well or they can be used badly. You can make smart decisions or bad decisions with them, and you can design them poorly and mess stuff up in both cases. In particular, the issue of the order mattering becomes a big thing, and they have to be exhaustive. They have to handle all possibilities, or you get runtime errors. In the case of guards, we can check multiple features of a variable, like that the length of our list is greater than 2 and that its first item, the item at index 0, is equal to the number 2. We can check both of those in the same condition. We get, therefore, more options for tests, like calling to other functions to check on features of our variables, of our parameters. And we can ignore variables. We can ignore parameters that are given to us simply by not including them in the conditional statements that are used. On the other hand, patterns can set up these variables automatically. They can name something X through the pattern, or they can name the whole list L and the head of the list X and the tail T, or whatever, multiple different pieces of it to be able to do different work with. automatically in the way that the pattern is structured. It gives us often a more condensed syntax. Again, that example of showing the empty list versus null L or that kind of thing. It can be more condensed in its syntax. And we can ignore variables more explicitly by using the underscore. So there it makes it clear that we have attempted to ignore that variable versus we may have just forgotten to include that variable in our conditional statements. So there are positives and negatives to each of these approaches, and you may find cases where one fits more naturally than the other. And I hope that you find them useful as you write your Haskell programs and try to handle more and more complex situations with your functions.